Hello everyone. In this lecture we're going to examine a very important arrangement of resistors, and this arrangement is called resistors in series. It's something that is very commonly found in real-life circuits, and that's the first reason why we will examine that. It is also something that really sticks to most electrical engineers' minds. The results that we get from that are so intuitive that one can really think that this is probably the most obvious connection we can ever make. So let's go ahead and examine that. In this circuit, I have shown you exactly what I mean by connecting resistors in series. We have these resistances R1, R2, all the way up to Rn, and each one of them is connected back to back. We have a cascade of those resistances such that we form a single loop. Now, that single loop is excited by a voltage source right here, and that is an ideal voltage source. Typically, the voltage V is known, and one of the things that we can find is the current I. Now, the way that most people think about having a bunch of resistances connected in series is that they can go ahead and replace them with something that they will call equivalent resistance, or REQ for short. But what does it really mean to replace them with an equivalent resistance? It means that if you were to put these resistances here in a black box, I'm showing it schematically right here, and if you were to put also that equivalent resistance in a black box, so you couldn't really see what you have in there, then as far as the source is concerned, the results would have been identical. What does that mean? It means that the amount of current you would draw from this source would have been the same in both cases. So the source really couldn't tell which of the two scenarios you have. You would draw the same amount of current whether you had those N resistances in series or whether you had this REQ. So that is really the fundamental understanding of REQ, of equivalent resistance, and this is something that we're going to talk again in a future video. But in order to proceed from now on, I want to write down an equation that defines REQ. So REQ, based on what I just described in words, is nothing else but the voltage V divided by I. That little triangle that you see on top of the equal sign simply means by definition. So in other words, REQ is something that by definition is equal to the voltage drop across over the current that you draw from that source. We're going to use this definition to find R equivalent here, and I will do that in the next slide. But the main reason we're discussing resistances in series is because REQ has a very intuitive expression here. So let me write down this expression, and then we will prove it. So the REQ, the V by I, in this particular instance of resistances in series, is nothing else but the sum of all resistors. So that's one of the reasons why this one really sticks to people's minds, is because it appears to be so intuitive. Now you might say, how can you derive that? Well, we can derive this by applying KVL, by applying Kirchhoff's voltage law. After all, we have a single loop here, and we have the voltage drops across every single resistor. You can see, for example, V1 across R1, V2 across R2, with the polarities you see in the figure. So, if I were to apply Kirchhoff's voltage law, I would start from my lowest left corner here. I would move clockwise in this loop. Then I would be able to write that negative V plus V1 plus V2 all the way to Vn with the polarities I have will be equal to 0. Another way to write this is that V is going to be equal to V1. But if you check V1, I have a passive sign convention. I have my current I1 flowing into the plus sign of V1. So I can use Ohm's law and write that V1 is equal to I times R1. Then similarly for V2, I have the passive sign convention. The same amount of current has no choice but to flow through R2. Remember the analogy of water. For DC circuits, currents flow more or less like water. once it exits R1, it has no choice but to continue propagating through R2. So this could be equal I times R2 plus all the way to I times Rn. So by writing it this way, I can very quickly find out what is the V by I, which was the defining equation for Req. So if I divide here both sides with I will have that V by I will be equal to R1 plus R2 all the way Rn, which is exactly the result that I mentioned before. So the derivation for the resistances in series situation is shown in the slide, and the result is that the equivalent resistance, the resistance you could replace all of these resistors with and leave the V by I relationship unchanged, is equal to the sum of all resistors. Now, in addition to this equation, which again is something that most people really easily remember, there is a second very important result that I would like you to memorize. And that very important result has the name voltage division, or sometimes people will call it a voltage divider. So voltage division is essentially nothing else but the equation that you can derive for any voltage drop across this arrangement of resistors. Let's, for example, pick here V2. The same result will apply for everything else. If somebody says, now that you know the results, can you really find me what V2 is? I could easily write down that V2, based on Ohm's law, as we did before, is I times R2. But I, as we just learned before, will be nothing else but V, the total voltage that you apply, divided by the total resistance. We found this before, R1 plus R2 all the way to Rn, times, of course, R2. Or if I write this slightly differently, I will have that this is going to be equal to V times a fraction, which is R2 over R1 plus R2 plus Rn, or R2 over Req times V. So when you read the equation, when you read it the way I have written it here, you really can't help it but think of this thing as a voltage division. So you took the total voltage that was applied and you divided this by a ratio, and that ratio is nothing else but the resistance you care about over the total amount of resistance. Or another way that people will say that is that the voltage drops will be distributed according to the values of the resistances. So a higher resistance will see a higher voltage drop across it than a lower one will. Again, this appears very intuitive and is a very easy thing to remember. So the voltage division, even though it's probably less often quoted than the series equivalent resistance, is as useful, and you should memorize it because we're going to be using it many, many times. So to summarize, in this video we have seen two very important results. The first result is how do I find the equivalent resistance for resistors connected in series. The second result is how do I calculate the voltage drop across any resistance, and we're using the voltage division formula. So thank you very much for watching this video. We'll be with you again next time.